I want to introduce here what resiliency is. So, in a distributed world where systems fail, we have networks kind of going down, power outage happening, disk going slow, packet drops. In all of it, we have some known failures there, and we build our systems based on how the systems are designed to fail or expected to fail. Resiliency is more about you do not know how the system is about to fail, but you want a system to behave predictably even in unpredictable situations like this, right? So it's basically bouncing back from where your system was and then making sure it continues to operate normally even in those unpredictable situations. For the next 15 minutes, I'm going to probably take you to a journey where we start with a basic OpenSearch cluster, take you all the way to a cluster that is considered to be highly available and resilient. So stay tuned. I'll briefly introduce an OpenSearch node and how the anatomy looks like. So a few basic parts as to what roles and functionalities an OpenSearch node kind of performs. Uh, First is cluster manager, a very important role here. Performs some metadata operations, making sure how to place the shards on different nodes such that the cluster continues to operate seamlessly. All the index creations, metadata updates, all of them kind of gets coordinated well, and other background operations as well. One of the cluster managed nodes is a leader that is elected by a algorithm which is based on Raft, and that basically takes on the role of a leader and coordinates all those actions. Next up is coordinator node. It's nothing but a request router, which internally takes care of routing the request to a specific shard. Also performs few search phases, but it knows where to kind of send your request to. And the last one is a data node, which actually hosts the shards, and it performs the actual heavy lifting. It does the indexing operation. It performs the actual search phases and rolls those search results up the coordinator. So this is the simplest setup, and that's where we began our journey into setting up a resilient cluster. So from the looks of it, right, we can see if this node, the various things that can happen to this is the hardware can crash, right? And boom, like what do we do? And all right, not bad. We need to be prepared for this, and so we have a two-node setup, and it looks great, right? There's no single point of failure, and let's check how we fare through this. So, do we have a single node failure resiliency here? Oh, maybe not. Let's see through this, right? So, for a two-node setup, what we have is even if one of the nodes kind of fail, the quorum apparently goes down, and you need both the nodes to be kind of serving to make sure the cluster is up and available, right? So it bears the same fate as that of single node and fails to operate seamlessly if one of the nodes even go down, right? So what next? Multi-node, right? Let's add a few more nodes to the mix, and now we see this not a single point of failure at this point, and things look good, not bad. What could possibly go wrong, right? Let's check a resilience check. Single node failures, yeah, good. But before I move ahead, if we want to configure a cluster, we specify, hey, what zones should the provisioning manager go ahead and provision the nodes in? If you do not specify anything, the infrastructure provisioning might choose a zone based on its will. And probably cases like this, wherein it can choose to place multiple nodes in the same zone, will bear the same risk as a complete zone going down due to a power outage or a lightning strike. And those failures are pretty normal, right? So when those failures kind of happen, we get into the same problem, which means the cluster isn't available anymore, right? And then to solve these problems, we explicitly say, hey, to the provisioning manager, hey, this is what you need to do. Pick this node, put it in a zone such that it's an isolated boundary. Do not place multiple nodes in the same zone such that each one of them have their own failure mode isolations. And clusters can continue to work even if one zones kind of fail, right? Quick check again. Single node failures, we are good. Single zone failures, we are good, right? Moving on. Now, what happens if we have a failure in a single zone here in a multi-zone setup. Typically, if you see when even if you place your hardware on multiple zones, the moment a single zone kind of goes down, shards try to rebalance, creates overhead on the remaining set of nodes, and now the entire traffic that is destined for the 3 nodes in the cluster that you see now gets redirected to the remaining 2 nodes. As a result, there is a churn in the cluster, there's an overhead, shards kind of start to moving in around those remaining nodes. So that doesn't offer you a predictable performance, right? When this happens, maybe your performance will degrade, maybe it might be acceptable for some time, maybe if not, and then we'll see. There's some approaches to deal with such failures, and as you can see, like you could deal with it reactively, or you could be more proactive about it. So the way to deal with, I mean, how users can deal with it reactively is go ahead and provision a node, another node, and say, hey, I had 3 nodes to start with. Let me, now that one node is something that is lost, let's go ahead and add one more node to the mix, right? But again, I said there's a churn here, and then we're not prepared for failures. The proactive approach is we provision to a point such that when the hardware failures happen like this, once like this, the system continues to operate normally, as if they were already prepared to handle this, right? And that's a proactive approach, which I would call as static stability. So it's the ability of the system to continue operating normally, even in this mode of failure, right? And that's where we need to design a system such that we've kind of planned for unknowns. We know systems will fail due to code bugs, hardware failures, power outages, and these are pretty normal. And the applications that are built on top of it don't necessarily have to know whether there have been a failure, redirected, scramble to get the hardware up, rebalance the whole thing, and create a deal with those churns, right? So that is what static stability was all about. One way to accomplish is something like this, right, wherein you reserve a zone, a couple set of nodes, and you call them standby. And what the standby zone is going to do is going to take in the write traffic. It's not going to serve the read traffic yet. Read traffic will be served by your, what you see is the active zones on the left, zone A and zone B. They'll be taking all the read traffic, and once we have a failure in, like, say, zone A or zone B, or even zone C for that matter, you'll have a guaranteed capacity that will be running all the time. Like you'll have 2 out of 3 zones almost running your read capacity. So you kind of get more predictability here. You know what might happen if a single zone kind of goes down or a single box kind of goes down. It's almost planned, right? And applications do not need to know about it. Quick check again. We are good with single node failures, single zone failures, and they are statically stable, right? Good. Some applications kind of require a really high availability, right? If you have multiple zones failing at the same time, these are like very rare though, but not to say it cannot happen. We can have a natural disaster. It could be a human error, a kind of deploying something, and yeah, and one of your clusters can magically kind of go wrong, and you probably haven't planned for it. But where availability is a very high tenet and you cannot compromise on it, the architecture that we could do is having a multi-region cross cluster, wherein we have a leader cluster and a follow cluster, and it's kind of working in an active passive mode. The leader cluster takes in the reads and writes both. The reader cluster on the other side, on the right hand side, basically just serves the read traffic. And the moment there's a failure in the primary, we cut over to the failover cluster. So pretty much good here. And let's check again. Single node, single zone, statically stable, and multi-zone failures. Pretty much good here. But not about it, right? There are multiple things more that we need to think about. The class of failures that I'm talking about are mostly failures that can happen instantaneously. Nodes will crash, and you'll see the failure almost coming up instantaneously, and you know about it, right? I'll talk about what the system sees it versus what the workload is kind of seeing it. Or the client side numbers are kind of showing up. They might be deceptive. Some system might say, hey, you know what, everything is all good, everything works fine. But it might so happen that the client is seeing a degraded performance, that the monitoring is not able to catch, right? And that turns out to be the gray failure right at the top, wherein the system thinks it is fine, but it's not so, right? Because there are slow failures that can happen. Your EBS can slow down. The network that you're talking to, right? They can start to drop packets off. So there are multiple things that can happen during that process. And our systems might not be able to detect it because it's kind of very hard to kind of go ahead and figure out what is the right thresholds when you fail the system. You have to get a really fine balance between when you want to fail the system or when you want to operate versus what the expectation from the system is, right? And no matter how resilient we kind of build the software, there'll always be points wherein we are not able to predict things like ray failures. And again, as I said, we need to plan for it. So what do we do, right? On an OpenSearch cluster, right, if you have the cluster provisioned as a statically stable cluster, you have mechanisms to do. You could either choose not to do anything, wait for the outage to kind of recover, but then you have to pay the penalty of degraded performance all through till the recovery happens. Alternatively, what you can choose to do is isolate a problem. If you have isolated the problem to a zone, this is what you can exactly do. You could do a read failover wherein you pass in, hey, this is a zone I think is not working and my cluster is kind of degraded. Let me weigh away my traffic and evacuate that zone such that all my traffic kind of now routes to the set of nodes that are healthy, that are considered healthy by my system. And you can do it manually as well. You can have an automated system that does it, but you still have your tooling up your sleeve, and you can always excite it manually to understand, hey, this is what I need my system to be doing. There were gray failures, I couldn't detect it, but yeah, I can always cut over. And that's how you perform your read failovers. On the bottom, maybe it's not visible, but there's a mechanism to decommission an entire zone. What it'll do is it'll cut off all traffic to the destined nodes. It'll sever all the connections off from the healthy zone to the unhealthy zones. It will make sure today that if your write traffics are kind of going to a zone that is considered degraded, it will stop all the traffic there. It will make the shards to fail, and it will make sure that the writes are kind of unblocked. Today, what happens is when you're sending a request to the set of data nodes, they'll synchronously replicate the data. And a single write path impairment in the whole chain, primary to replica, and to all the copies from there on, right? Anything that chokes up there is going to be a single point of bottleneck for your system. Even though systems might behave fine, they might see an additional degradation over time, and that may lead to a churn in the cluster, eventually taking the whole cluster down, because system will continue to try to do a back pressure. If the incoming load is too high, maybe the system will not sustain it. And that's why you need something like a write failover to happen. And once you kind of isolate the zone, you might want to issue a write failover, and you kind of almost instantly get a recovery there. So there are various tunings over and above what we talked about that can be done to kind of have a protective guardrail in the systems, both on the client side, server side, and how we balance the workloads. On the client side, what you have is metrics. I think this is the very important part that I want to talk about. Having a good level of metrics and visibility, I think, is the first thing that needs to be there. Once you have a good sense of how your application is behaving and what is the acceptable latency, just have some measure there. And that is what you could use when you configure your retries. You should configure multiple retries with a backoff such that the overall backoff time doesn't go beyond your acceptable latencies. Choose a number, let's say a P19 latency, and make sure your retries kind of well fit in there. And you know how your P19s are going to look like, and you can accordingly configure it. What you can additionally do is, if multiple requests are returned at the same time, this is a good mechanism to have a jitter there. And once you have a jitter, not all requests will be retrying at the same time, which kind of renders a high probability that the retries might go through. Retries should not always happen exhaustively. I think there should be a capped retry to make sure that the system is only ever doing a productive work, and things that the client is kind of going to go drop because there was like too many retries and the system is not able to still churn out the response that the client was looking for. It's better for the client not to retry because it's only overloading the cluster there. Uh, timeouts. Timeouts are a very good mechanism to kind of give an indication to the server as to, again, what your acceptable latencies are. Now, if you give that pass on the hint to the server, you probably are saying to the server, hey, you know what? This is a time which is acceptable to me for me to consume a productive work out of you. The moment you kind of go beyond this limit, please do not work for me. Go ahead, do your cancellation. I do not need this work anymore. Maybe you can just recover and sit back because I'm anyways going to drop it, right? Because it's not acceptable to me. So make sure you use the right retry mechanism and timeouts. These are very important, especially in the midst of failures when your system is kind of getting overloaded. If you do not have retries and timeouts kind of configured, you'll probably potentially only overload the cluster. Load balancing, again, is a very important mechanism here. Anytime you have a health detection mechanism that says, hey, the node health is not doing fine, or let's say some IPs are having connectivity problems, it's better not to kind of use the same IPs when you're sending the request. It's better to penalize those connections. Make sure that you are sending your traffic uniformly across the set of healthy IPs that your system has determined. It's always good to kind of check on what your set of healthy IPs are, and make sure the number of connections is kind of contained. You're reusing connections as much as possible, because there's again a performance penalty as to if you're kind of increasing more and more connections, it's holding back the file descriptors on the server side as well. These are system side tunings that is probably important to make sure that the clusters are resilient enough. Fault detection pings are a good way to do a liveness check, and we should not be too aggressive to kind of fail the request if things don't work fine. We always need to be planning for garbage collection pauses to happen, and it's very hard to disambiguate between a garbage collection pause and an actual network failure, and which is why you need to make sure that your system, the maximum GC pause time that a system can probably tolerate, is what you should probably configure your fault detection pings to. Because even there, if there is no network packet drop or there's no network outage as such, your GC pause is going to make the system feel that, hey, there's a problem in the network, and probably it'll keep on failing or tripping the request now and then. Local health checks are not a liveness check. It doesn't tell you whether the server is there or not. It basically tells you, hey, your dependencies that you have fundamentally, are they up? Are they running fine? Is your file system up or not? Do you have permissions on it or not? If a cluster state update has to go through, will it go through or not? So these are good checks to be in place, and it's good to do a startup check and perform those. What you can again have is, again, when I talked about gray failures, there's mechanisms here where you can set the timeouts on the health checks, and you can say, hey, beyond 60 seconds or beyond 30 seconds is where if my file system is going to take time, I probably mark my host as like unhealthy. And that's pretty good, right? Because if your this are slow, there's no point for the system to operate in a severely degraded mode. It's not going to help anything. It's only it's going to slow down the system organically. JVM configuration, I think a lot of users here probably have gone through like CMS, G1GC. One thing to understand there is we have IHOP in the most recent G1GC configurations, and that basically starts off with some initial runs of the cluster. So basically, you give an indication as to when the GC or the main garbage collection is supposed to happen, which is what you indicate using a G1 reserve %. But that is only a hint. What really happens behind the covers is it's kind of adaptive in nature. It'll adapt based on your workloads. So anytime you have a change of your workload patterns, feel free to visit your JVM configurations, because it might not work the way you expected it to. And you need to tune them to get the best out of the performance there. CPU, again, is a very important one here. We have seen sometimes there are multiple processes running on the same box that you're running the OpenSearch process on, and some of the processes are kind of eating into the CPU cores, right? It's a very good practice that you use C groups to ensure that you are able to limit how much CPU is kind of expected out of other processes, so that no one process is unjustly stealing the CPU cycles away. Yeah, lastly, disk watermarks. These are basically around your shard sizes, how many shards you want to be, how big of a shards do you have, and what is acceptable when like recoveries or rebalancings are happening around. And when you have disk watermarks almost very close to filling up your disk, and you do not have it configured correctly, it will end up in a write blocks, because that's a defensive check the system will do eventually. And when that happens, it's almost good as unavailability, because you'll not be able to do a writes here, and your systems are almost going to fail for all the writes that happen. Reads might still go through, but yeah, availability is still a concern. So make sure you watch out for these parameters. I'll briefly introduce on some of the mechanisms that we've been working on over the couple of years now, and what are the mechanisms that we've come up with to kind of improve the resiliency to ensure that we're tuning the workloads right, getting the right mechanisms in place to reject overloading, load shedding. So one of the mechanisms there is both in the indexing path and the search path, and we'll talk about it. And the third is that I want to cover is cluster manager task throttling, which is very important because cluster manager is, again, you see there's a single leader that operates off, and if that leader is kind of overloaded, so what it's not able to make a meaningful progress. An index creation happens, it's already overloaded. Your bulk requests are going to stall just because the cluster manager is overloaded. So you need to make sure that the cluster manager is ever doing right about a zero queue or a very small queue size, because it's important that some of the critical requests go through and those don't get stalled. Shard indexing back pressure, I think this is something that we introduced last year around. And this is a very good mechanism to kind of selectively check on the indices, shards that are placed on the nodes, to make sure we are making a fair judgment to fail only a specific shard if a node is in duress, to make sure that other shards are still going to take enough write requests and we don't end up failing the entire node. Failing the entire node has got like problems with too many recoveries happening, and when it's a workload problem, we need to be like very selective about it, making sure that when we apply fairness in the system, it is at a shard level. And the system is able to kind of adaptively adjust based on certain thresholds that we've configured, which is around elapsed time. If the primary is taking more time or the replica is taking the same more like 2x or 3x the time that the primary probably took, and the throughput is kind of varying. Based on that, it will adaptively select, hey, is there a degradation that is happening in the cluster? If yes, can failing the shard is the right thing to do. If it has enough evidences to do so, it will go ahead and fail the shard, and the cluster will recover. That's what it tries to do. But till the point it tries to kind of do a firefighting, make sure that the node is not getting overloaded, try to push back on the coordinator so that if no incoming traffic is coming till the existing work is kind of not finished up. So by default, it's disabled, right? And there are a lot of tuning parameters here. I'll recommend we go ahead and enable it. It's not kind of visible, but it's called shard indexing back pressure enabled. That needs to be set to true. If you want to try out this feature, do try it out. There are a couple of more configurations. You want to tune it based on your workloads. Surge back pressure. Surge back pressure is something that we needed the most. So we have circuit breakers and admission control, but the bigger problem with that is, while it works for most scenarios for a bulk, because the front load throttling works for bulk because we know what the payload size is, and the payload is big, we probably will not admit, and the circuit breakers will kick in right there. The biggest problem with searches is you'll never know at the time when you're admitting those requests, what is the actual cost of the query, right? And once the query kind of comes in, it kind of does a, let's say, wildcard search or a very expensive aggregation, nested aggregations. You'll see the memory kind of go and pile up a lot, right? It'll create CPU churns in system. It will not allow other meaningful productive work to kind of go through, and you'll always see your system churning out something. And that is where we kind of brought in surge back pressure to understand if a single request is it going beyond a threshold value that is configured for a single request. And if the single request is kind of taking more than like X% of the total CPU or the X% of the total memory, and it is kind of running for a decently amount of time, we go ahead and cancel that search request. Those might be some of the rogue requests. If the workload kind of wants those requests to kind of go through, there's a bunch of tuning parameters that you can adapt based on your workload. You can set that to give surge back pressure hint as to what is an acceptable workload that you want to run, and the surge back pressure will make sure that it is allowing those requests to kind of go through. As I talked about, right, it probably does a cancellation score, and based on a score of the bunch of concurrent queries that are running, it will start to pick the one that is kind of having a highest cancellation score, go ahead and cancel it, go next in the line, see if the system has recovered. If not, go next in the queue to pull up the next in the cancellation score based on the score that it kind of comes up with. And at some point in time, when it realizes that it's doing too many calculations, it will kind of back off because it knows that it's not probably doing the right thing. There's a problem somewhere else in the system, and it probably is getting deceived by thinking that, hey, this is the system that is causing too much churn in the system. And again, this again not enabled by default. You can set it to search back pressure mode as enforced. Cluster manager to task throttling. I think this is one of the major parameters that we should look at to avoid the task pileup to happen. So there are multiple tasks with the same priority that runs today. There could be like a put mapping request. There could be, let's say, a shard started event or a shard failure event. Shard failure and put mapping are high priority items on the pending task queue. And if you want to isolate each one of them and say, hey, put mappings is a higher priority for me than shard started shard failed, you could configure it accordingly based on your task type and your throttling limits so that you have very granular control as to how you want the system to behave. A single queue is not probably fair enough to in its current incarnation to kind of provide you granular controls as to how you want the system to operate. And this is like a very crucial setting. You might want to try it out as to what your workloads are best suited for, and accordingly configure a task type, which is nothing but, let's say, shard started, shard failed, node join, and you can put how many concurrent requests are allowed to stay in the queue, which is your threshold limit. Monitoring is very essential. We need to keep monitoring the system, but also be prepared for failures. Cluster JCPO, JVM are kind of good performance indicators as well. They also kind of, if you put early alarms in the system at a reasonable amount, let's say 70% or 80%, they can still give a good indication as to where your workload is going. Do you need to scale in, scale out? Do you need to kind of put your back pressure mechanisms more aggressively? So all that indication is going to give, you're going to get probably after monitoring clusters when you put them on. GVM PEM pressure, similarly disk performance. For disk performance, I also want to talk about like when the disk actually gets throttled, it not only kind of has a performance problems on the actual write and read request, it is also stability risk because cluster state is also one of the writers that go ahead and write to the disk, right? And you need to make sure that the throttling due to workload is not kind of eating up your IOPS on the disk that kind of starves even the cluster state update to kind of go through. So keep monitoring there. File system need to be always verified on whether they have the right permissions, they are read-only or not, free space, do you have enough plenty of free space, you need to scale in again or scale out. Thread pool queue is given an early indication as to which way things are going and is the system able to keep up or not. Errors and latencies, I think I previously also called out, I think these are good indicators for your health checks, and probably you should use a good load balancing mechanism to make sure you use nodes that are kind of performing good. All right, so what's next? Before I dive deep into this, we've been thinking for resiliency for quite some time, and what we realize is, can we do better at what it is? What if a single node cluster can be made more resilient to more outages? Wouldn't it be good if a single node can survive some failures and be able to again bounce back, recover from the state where we left it off, and still be able to take more requests? Or for that matter, the node can be replaced by some other node and can pick up from where the previous node left. With those things in mind, I think we designed the remote backstore and remote back metadata. Some of it is in flight though, but what you can kind of expect from this is even the single node will have a higher resiliency. It will have a very fast recovery time, which means you can run smaller workloads on single nodes and not have to worry about data being lost there. Even if the data is lost, you can spin up another node and kind of rehydrate from a remote back storage, and you can continue from where you left off. So that's a good addition to the overall resiliency picture. Extensible health checks. We realize that health checks is not too exhaustive. For example, we do not have a good check on the network packet loss, and which is kind of important for not only performance, but for overall cluster stability as well. Admission control is something that is a lever above, and that's the front load throttling. And a lot of measures need to be put there, and that is something that is also in flight. We're trying to make sure that not only the rest layer, but at the transport layers where we have node-to-node communications happening, admission control kind of kicks in and sees, hey, if there is a node that is already overloaded by regard to like CPU, memory, JVM, all these parameters, it kind of goes ahead and kicks that request, stops that request from being admitted into that node so that it's able to kind of keep up. Disk guardrails, we've kind of realized that if disk kind of gets full, it not only impacts the write availability, but sometimes it's also causing churns in the cluster because your cluster metadata updates won't go through. Your disk is probably will not be able to survive the writes that is needed for the cluster state update to go through, and that will result in the eviction of that node from the cluster itself. So enough buffer has to be put in there, and we are looking at some merge policies around that to make sure that whenever a merge failure happens, they're doing a good cleanup of those leftover files such that they're not counted as accounting for more disk space, and let the systems kind of recover quickly. Smarter clients, the Java client, we kind of look forward to is kind of having more smartness in, wherein before even sending a request, it gets a sense of the back pressure, the queue length, the adaptive mechanism that it could use to understand, hey, which nodes could be preferred over which other nodes, and smartly route traffic to the set of nodes. With that, I end my talk. thank you everyone for joining in.